All right, hello everyone. So welcome to the next lecture. And once again, Learn is letting students into the room. So let's wait a few seconds for that. Okay. So I think a bunch of people are here now. So I'll start. Okay. Okay, so today I'm trying something a little different with Learn. So it turns out that if you do a screen share in Learn, it uses better video quality than the webcam, and so that's what I'm doing today. So I have my camera on the screen, and then I'm doing a screen share of that. So you probably notice that the frame rate is low. So, you know, if I wave around, you don't see motion very well. But the flip side is that you should be able to see the whiteboard much better, hopefully. And so I'm going to try it this way for this lecture. And then you can tell me, you know, afterwards, like, you know, is this okay? Is this terrible? So we'll try it for today and possibly do something different in the later lectures. One thing that I'm considering is moving away from Learn to something like YouTube or Twitch. And the worry there is that, you know, those platforms are blocked in certain places. And so I want to know if that's a problem for anyone. So, you know, is there anybody here attending the live lecture today who would not be able to attend or to view YouTube or Twitch? So, you know, are you in a place where those are blocked, and are you here now attending the live lecture? Because I can always provide the recorded lectures, you know, through other means, but it's really just the live lecture that I'm considering putting on YouTube. So if you're here, you know, if you're here and you wouldn't be able to be here if we were on YouTube, you know, please say something, or please send me an email. And you know, I'll take that into consideration. And then, you know, after today, if you think the video is really terrible and we can't do this bongo thing, do let me know that as well. Okay, so let's try this and we'll see. So, all right, so today I want to look at parsing, and so the general idea is that your compiler starts with a sequence of characters, then it goes through the scanner to get a sequence of tokens. Okay, and I've got one person with frozen video. Anyone else with frozen video? Okay, so hopefully that's just okay. All right, so hopefully that's just one. Just a special case. Okay, so all right, so your scanner gives you a sequence of tokens, and then now we're going to use the parser to take that sequence of tokens and give it structure in the form of a parse tree. All right, and so for scanning, we used regular expressions and regular languages. For parsing, we're going to need something more powerful. We're going to need context-free languages. And the reason is that in the parser, we want to be able to recognize nested structures. So, you know, things like nested expressions, or blocks nested within other blocks, loops nested within other loops, and so on. So for nested structures, we need context-free languages. So that's the real motivation. So nesting requires CFLs. Okay, and so you've hopefully, at least the term context-free language isn't completely new to you, but I'll do a review of context-free grammars. So a context-free grammar G has this for tuple with 4 components, and different people give them different use different letters for them. So I'm going to use N, T, R, and S. If the writing is if the writing is too small or not visible or still fuzzy from Learn, tell me, but hopefully it's readable. Okay, so we've got these 4 things. Non-terminals, so non-terminals N. Okay, so N is a set of non-terminal symbols. Then we have a set of terminal symbols, T. And so the terminal symbols are like the alphabet. These are the symbols from which the strings are formed that are the strings in the context-free language, right? So just like a regular language, the context-free language is a set of words, and these words, in this case, are strings of these terminal symbols. Okay, and then productions or production rules. So production rules R, and I'm going to write that R is a subset of N times V star. And so here I'm trying to say that each production rule has one non-terminal and some sequence of symbols V, and I didn't define symbols, so I should define symbols V as terminals union non-terminals. Okay, so each production rule has a non-terminal on its left-hand side and some sequence of terminals or non-terminals on its right-hand side. Okay, writing is perfectly readable. Okay, that is a good sign. At least we're getting something for this lagginess. Right. Okay, so symbols, production rules. What do we have here? Okay, and then so NTR, and then the start symbol S. So the start non-terminal. So S is one of the non-terminals, and you have to specify the specific start symbol. Okay, and I'm using this star notation, and you'll see me use it over and over again to denote a string of symbols from a set. So in this case, it's a string or a word of symbols from the set V, which is the terminals and the non-terminals. All right. So stop me if there's questions. It's very common when we're talking about grammars to define some sort of convention for meta variables that stand for these various symbols. Okay, and so the idea is, I don't want to, every time I define something or state a theorem, I don't want to always have to say, let A be a non-terminal, and let capital B be a terminal, and so on. So I'm kind of going to state that once and for all up front. So my convention here, so I'll say convention So if I ever, say lowercase letters A, B, C, if I don't introduce them, I'm going to assume that those are all non-terminals, right? So those are all in the set N in the set of non-terminals for my grammar. And I'm going to, make the same kinds of definitions. They're like running definitions, right? This is always the case. So for terminals, I'm going to use capital letters A, B, and C. Okay. And, this is a convention that comes not from me, but actually from Donald Knuth, who did a lot of work on context-free grammars a long time ago. And like almost every textbook follows the same convention. So, it's not just for us. Okay, so then a production rule. I really should skip production rules. I'll come back to them. So let me do, symbols. So if I want to have a letter that is either a terminal or a non-terminal, I'm going to use uppercase letters from the end of the alphabet. And then, so a convention for the start symbol is to use the letter S. And so because the start symbol is a non-terminal, I'm going to, by convention, make S also be a non-terminal, even though it's not near the beginning of the alphabet. All right, now to write production rules, I need symbols. So I have symbols. Those are X, Y, and Z. But I need strings of symbols. So for string of symbols, E star, here I'm going to use Greek letters. I mean, I'm out of letters, so I'm going to use Greek letters here. Okay, and so now for a production rule, I'm going to write it with an arrow. I'm going to write the non-terminal, let's say A, arrow, and then the string of symbols alpha. Okay, but the point is, if you ever see an alpha, it means it stands for some string of symbols. And there's one more that I want to add here: strings of terminals. String of terminals. So that's going to be T star. So, we often want to talk about strings of terminal symbols because, for instance, the word or the input to our parser is a string of terminal symbols. And so for that, we're going to use lowercase letters near, I try to, it's hard to distinguish uppercase X and Z and so on. And, I'll also put W because, often you want to say W for word. Okay, so let me see. So I think there were questions. Aren't ABC terminals? So lowercase ABC are you're right. It's backwards. Something is backwards. NT, right. Okay. Yes. Thank you for the question. And where did I put my eraser? All right. So okay, so non-terminals are going to be capitals. And terminals are going to be lowercase a, b, c. Okay, thank you for that correction. Flipped, yes, okay. It's all the same thing. Yes, okay, so I have those flipped. Okay, so we have these conventions. So any questions about the conventions or about the sets? And, now I'll start defining things with them. All right. So, so now, okay, so what does a grammar mean? right? So we want to define the set that the grammar represents. So this is going to be a language, a set of words. So I'm gonna, I want to leave these conventions up here for a bit. So let me go up here, and eventually I'll have to erase them. So we're gonna say that if I have beta A gamma, so if I have some string beta A gamma, then it directly derives another string beta alpha gamma if there's a production rule A goes to alpha in my set of production rules. Okay, and so the thing I'm defining here is this double arrow, and the way that we pronounce that double arrow is directly derives. Okay, and so the way this definition works is that it says, well, if I have any string of terminals and non-terminals, right? So here, beta can be any terminals and non-terminals, and so can gamma, and that string has some non-terminal A, somewhere in the middle of it. Then if I have this production rule, A goes to gamma in my grammar, then this string with the A in it can derive the same string, but with the A replaced with alpha, right? So I can apply the rule to any non-terminal symbol that appears in any string to expand that non-terminal symbol. Okay, and so, hopefully, do ask questions if that's weird or new, but hopefully you've seen that somewhere. And then we want to define the reflexive transitive closure of directly derives. The idea is I want to be able to take multiple derivation steps. So I'm going to say that alpha derives beta, and I'll write that as the arrow with a star on it. So you can say if alpha equals beta, or alpha directly derives some gamma, and that gamma derives beta. Okay, there's various ways to define that, but the basic idea is I want to say if I start with alpha and I take some number 0 or more directly derived steps, I will get to beta. Okay, so and this is called derives. Oops, all right. So this red pen doesn't work. Okay. All right, so questions, no questions, everything's good. All right. So now we want to define the language. Before I define that, let me define one more thing. So I'm going to define sentential forms. So I'm going to say if S derives alpha, then alpha is a sentential form. Okay. So, so here S is the start symbol of my grammar, right? So, if I had more space, I would say, S has to be the start symbol of my grammar. So the idea is that a sentential form is any string of symbols that can be derived from the start symbol. Okay, and it's alpha, so it can be any symbols. It can be terminals and non-terminals. All right, and so we're going to use that in our parser to see what are all the things that can be derived from the start symbol, and then, some of those sentential forms, might lead to the input that we're actually parsing. Okay, so a sentential form, anything that's derived from the start symbol, but it can have terminals and non-terminals in it. Okay, and then, so really my language that is generated by a grammar is going to be all the sentential forms that only have terminals in them, right? So I'm going to say the language of a grammar is, you could write it as the sentential forms of that grammar, intersected with the set of strings of terminal symbols. Okay, or sort of the more common way of writing it is just as a set of all the words, right? So I can say X is a string of terminal symbols, and I have to specify that it's only terminal symbols such that S derives X. Okay? So sentential forms can have terminals and non-terminals, but the language specified by the grammar is consists only of terminals, but it's all strings of terminals that can be derived from the start symbol X. So all strings of terminals that are also sentential forms. All right, and we've got a question. So what is the difference between a terminal and a non-terminal? It's my first introduction to CFGs. Okay, so I wanted to go fast, and I assumed that it's nobody's first introduction to context-free grammars, but okay. So let me. So I have an example coming up. Let me just see. Yeah. Okay. Yeah. All right. Let's do this then. Okay. So I'm gonna erase this. The conventions here. Let's look at an example grammar, and typically just for shorthand, we would use we would only specify the production rules. So let's say I might have a grammar where there's A goes to B, G, C, and so here A and B and C are non-terminals. G is a terminal. Okay, and I've got B goes to AB. B also goes to CD. And then capital C goes to H. And capital C goes to EF. Okay. All right. And so the non-terminals. So the terminal symbols are symbols out of which you will generate the words in the language, right? So the language consists of strings of terminal symbols. So in this case, they're the lowercase letters, right? So I could say, I could define the full grammar as, A, B, and, up to G. And the non-terminals in this case are A, B, and C. And the idea is that the non-terminals are only used internally within the grammar. So on the left-hand side of these production rules, and there are things that can expand to other things. So in the context of a compiler, the way you would think of these is the terminals are the tokens that your parser, that your scanner outputs, that are the input to your parser. So things like, if, then, else, all your keywords. Identifier is a kind of terminal, literals, and so on. And the non-terminals would typically represent higher level structures. So let's say a while loop or an if statement or a function declaration or a class declaration and so on. And the production rules tell you how you can arrange sequences of keywords or sequences of sort of smaller concepts to make bigger concepts. Okay, so you would have production rules that would say, a class has a sequence of fields and methods, let's say. All right. I think, all right, so just to finish off the example, the production rules for this grammar would be this set of 5 production rules. So I'm not going to write them. And, as a convention, well, I'm going to say that the start symbol for this grammar is A. And sort of the convention is if I write a grammar, it's very common to just write it. Hang on, I think I have a better red marker here somewhere. There we go. Okay, so it's common to write a grammar by just listing the production rules, because typically you can get all the information out of that. So all the non-terminals are on the left-hand side of rules, and everything else is a terminal. And then the convention is that you always list the start symbol as the left-hand side of the first production rule that you write. Okay, so really, to be formal, we should list the sets T and specify S and list R. But as a shorthand, you just write out R and make sure you put the start symbol first. Okay, so there's an example grammar, and let's look at some example derivations for this grammar, right? So in this grammar, I would say that A derives, well, and what does A derive? Well, there's this production rule that says A goes to BGC. So I would say that A actually directly derives BGC. And then now I have a string where there are 2 non-terminals, B and C. So I actually have a choice. So I can say that BGC derives, and now so let's say I choose to expand B, and now I have a further choice of whether B would go to AB or to CD. So the grammar allows me to choose. So I'm going to take the first choice, B goes to AB, and so there I'm going to say that the string BGC directly derives ABGC. Okay, but I could have also, and I'll kind of do this vertically, I could have also expanded the C and said that the C derives EF. So then I would have BGC directly derives BGEF. Okay, and so all 4 of these strings that I've written here, they are all sentential forms, because from the start symbol A in 0 or more derivation steps, I can get to any one of these strings. And if I wanted to go further, here I can expand the C to say EF, or I could choose to expand it to H, but in this example, I'll expand it to EF. And so now, ABGEF is a sentential form, but it is also composed only of terminal symbols, and so it's a word in the language that's specified by my grammar. Okay, so is it possible to have a terminal that is not a sentential form? And sentential form. Okay, so the other sort of okay, so someone's mentioning sentence in the chat, and so I haven't defined a sentence, So a sentence is an element of the language. So it's exactly a sentential form that is also made up only of terminals. So every sentence is a sentential form, but sentential forms can contain non-terminals, but sentences cannot. Okay. All right. So okay. So now I have so ABGEF is a sentence, and all of these strings are sentential forms. Okay, and I mean, the other way, or another way I could have gotten ABGEF is this way, right? And okay, and so the other concept here is the idea of a derivation, and a derivation is a sequence of these directly derived steps. So it's basically a proof. If you tell me, oh, ABGEF is in the language, and I say prove it, and you say, well, okay, it's made up of terminal symbols, and A derives it. So how do you prove that A derives it? Well, you give me the sequence of these steps, right? Or this sequence or this other sequence. And so both of these sequences are derivations. So I guess I could say, yeah. So a derivation is a sequence of directly derived steps. Okay. So a derivation proves that a word is in the language. And really, a derivation also tells you something about the structure or how it is that the start symbol derives that word. But I mean, usually when we think of parsers and we think of data structures in a compiler, we think of parse trees. But the thing is that derivations and parse trees, correspond to each other. So box things off here. So let's look at an example parse tree. And I'll do a parse tree for this ABGEF example. And so a parse tree, I would always have the start symbol at its root. So I would have A here. And then the property of the parse tree is that every node in the parse tree corresponds to one step of a derivation, and it corresponds to a production rule in the grammar. So in the grammar, I have a production rule that says A goes to BGC. And so, anytime I have a node in the tree with the symbol A, its children have to be, it has to have exactly 3 children, and they have to be exactly B, G, and C. Okay, so the grammar, the production rules, give you a restriction on what can ever appear in the parse tree, and so you can use that in your compiler after you're done with your parser and you have your parse tree. Later on in the compiler, you can say, I see a node A. What could its children possibly be? And your compiler is going to need to handle all the possible cases. So you would want to know what all the possible cases are. So in this case, the children must be exactly B, G, and C. Okay, but then you have another non-terminal node in the tree B. In this case, there's 2 production rules. So the node B could either have AB as children, or it could have CD as children. So in this, for this example, we will give it children AB, and similarly for the C, we'll give it children EF. Okay, and so in a sense, the parse tree is a graphical representation or a data structure that corresponds to the derivation. So in each step of the derivation, I used one of the production rules from the grammar. And so each step of the derivation corresponds to one of the nodes of the parse tree and then the children of that node, right? So I expanded A to BGC, I expanded B to AB, and I expanded C to EF. So those are the 3 steps in my derivation. So from a derivation, you can build up the parse tree data structure. From a parse tree data structure, you can read off a derivation. I guess one other thing I should mention is that the word that is represented by the parse tree, or really the sentence, right? The string of terminals is the sequence of leaf nodes of the parse tree. So the leaf nodes here, that don't have any more children, that's where you find the word that is being derived, okay, or the word that is being parsed. So the idea of our parser is, you will give it a word like ABGEF, or in the case of a compiler, you'll give it some sequence of tokens, and the parser is supposed to build this parse tree for you. All right, any more questions happening? No, okay. All right. So we have a parse tree, and we have derivations, and it's common to kind of treat derivations and parse trees as interchangeable. When you talk about parsing algorithms, sometimes in theory, it's more convenient to think of derivations. In practice, the parse tree is the data structure that you want to get out of it, but really they're equivalent. And so we kind of talk about whichever one is more convenient, right? If I'm writing formalisms in math, it's easier to write about derivations, which I've defined formally up here, than about tree structures. But really, they're equivalent. Okay, so one other thing that right, so parsing is, given, well, yeah. So parsing. Okay, so given x, find a derivation or a parse tree for x, okay, if one exists. Because, x might not be in the language generated by the grammar, and in that case, there is no derivation, because really the language is defined as the set of all sentences for which there is a derivation. Okay, but we want to generate this parse tree. Now, one other important concept is the idea of ambiguity. So, we're given x, find a derivation or a parse tree for x. In some cases, there might be more than one parse tree. And if there's more than one parse tree, then that's bad, because the parse tree is what the compiler uses to represent the meaning of the program, or at least the structure of the program. And so if I have a program that turns into 2 different parse trees, that's like the program having two distinct meanings. And you don't want that, right? You don't want to have 30 different compilers written by the 30 different groups in the class, and have each of them implement a different programming language, right? So you want the grammar to be such that the parse trees are unambiguous. For any input string, there's only one such parse tree. So So grammar is ambiguous if there exists more than one parse tree or some input X. Okay, so if there's at least one program X for which I can draw two different parse trees, then that's bad and my grammar is ambiguous. And so whenever I design a parser, design a grammar for a programming language, I always want to make sure that the grammar is unambiguous. Okay, and another reason for this is, let's say you have a grammar for arithmetic expressions. Typically, you want to make sure that the parse tree that you get out of an arithmetic expression respects the usual arithmetic precedence and associativity rules, so that you do multiplication before addition and so on. Right? So you want the structure of the tree to reflect how you are going to evaluate that expression. And if you have an ambiguous grammar, then maybe one parse tree for that expression does multiplication first, and a different parse tree does addition first. And you don't want that. You want the parse tree to determine the structure. Now, one thing, so I said, okay, so a grammar is ambiguous if there's more than one. And we always want unambiguous grammars. So more than one parse tree. And so how does that correspond to derivations, right? So I said that derivations and parse trees are kind of interchangeable and all that. So, here I have one parse tree for this string, but I really have two different derivations, right? You can go this way, that's one derivation, or you can go this way, that's a different derivation. And so, there's two derivations for this string. So is this an ambiguous grammar? And so the answer is no. So the definition is really about parse trees. But, how do we translate that into derivations? Well, the thing is that these two, even though they're two different derivations, they're kind of the same in the sense that the same the non-terminal symbols in those derivations are expanded the same way. So the C is expanded to EF, both in this step and in this step, and the B is expanded to AB, both in this step and in this step. So in that sense, both of these derivations correspond to the same parse tree. And the only difference between them is the order in which the different non-terminal symbols are expanded. So in this derivation, I expand the B first. In this derivation, I expand the C first. So it's really just the order. And we want to be independent of the order. And so we're going to say, equivalently to parse trees, we're going to say left derivations or right derivations. And so it's often also called a left canonical derivation or a right canonical derivation. But okay, so what is a left canonical derivation? So this is a derivation where you always expand the leftmost non-terminal first. So expand leftmost non-terminal first. Okay. All right, and then similarly, a right derivation is one where you always expand the rightmost non-terminal first. And the idea is, the derivations are the same except for the order in which things are done, and the order doesn't really affect the structure, right? You're still going to get the same tree. It's just, do you look at node B first or do you look at node C first? Okay, so as a way to fix the order, we're going to say, oh, well, you have to always expand things in this order. And once you fix the order this way, now there's a one-to-one correspondence between parse trees and left derivations, and between parse trees and right derivations, and so on. So there's more than one parse tree if and only if there is more than one left derivation, and if and only if there's more than one right derivation. Okay, so this is okay. So this is how we get from parse trees to derivations. So when we look at specific parsing algorithms, it's common to have algorithms that always give you a left derivation, or other algorithms that always give you a right derivation, just to eliminate the non-determinism that you would otherwise have in the algorithm. All right. Anyone else with any more questions? Okay. So I'm gonna right. So maybe it's kind of clear that we want unambiguous grammars. Great. So how do we get them? And now I'll tell you something a bit discomforting or annoying. It turns out that determining whether a grammar is ambiguous or not is undecidable. And so if you took CS444, you would have seen that there, hopefully. Hopefully they still teach that in CS444. If not, they should. Anyway, it's undecidable. So, you can't write an algorithm that's going to look at a grammar and tell you, yep, okay, that's unambiguous, you're good to go, your compiler is well defined. So that's kind of a shame. But the good thing is that there are algorithms that will determine whether a grammar is in some smaller class than all unambiguous grammars, and those smaller classes imply that a grammar is unambiguous. So we're going to see algorithms where if that algorithm says your grammar is okay, I can parse it, then that automatically ensures that your grammar is unambiguous. So you can think of these algorithms as tests for ambiguity that guarantee that a given grammar is unambiguous, but might reject certain grammars that would still be unambiguous. Okay, but I want to sort of stop with the definitions and start looking at actually parsing an actual algorithm. So left derivation, right recursion, and vice versa. So not quite. All right. So I mean, that's an interesting question. So okay, this wasn't something I was going to talk about, but it's important. So I just got to figure out where to put this. So in a grammar, in a grammar, you might have recursive rules. This grammar here was pretty simple because there was no recursion in the rules. But I can have a grammar that has a rule like this: A goes to AX, or a grammar that looks like this, like A goes to XA, or other rules that have A in the right-hand side, or not even a simple recursion, right? I could have A goes to, and I guess I shouldn't be using X because of my convention, so let's use B. but I could do like A goes to BB, and then B goes to, you know, AA. And so there, even though it's not a direct recursion, there's a recursion between these two rules and between A and B. So in general, I can have recursion in my grammar, and that's what gives them their power. And there's this idea of left recursion, of having the recursion on the left-hand side, sorry, on the very left of the right-hand side, so as at the beginning, and or at the right. And so the issue is certain parsers can only parse grammars that don't have certain kinds of recursion. But the idea of recursion in the grammar and a left canonical derivation or a right canonical derivation, those are two separate issues, right? So here, this is just a question of the derivation of which symbol I expand first in the derivation, whereas here the recursion is where the recursion happens in the grammar. All right. So if there's more questions, ask more questions. But I'm gonna pause 2 more seconds, and then I'm gonna erase everything. All right. Okay, so we are given a grammar and we're given an input string, and we need to build a parse tree for that input string, right? That's the parsing problem. And so, you can think of it, you can think of it as building the parse tree, but you can also think of it as, as building a derivation. And so, here's the problem, right? I give you a grammar, so you know what the start symbol of that grammar is, and I give you some input, some X, that's the input string that your compiler needs to parse. And so the problem is, find a derivation that a sequence of steps that goes from S to X, if such a sequence exists. Okay, so we need to find this sequence, this derivation. Okay, and so so how do you find a sequence? And I think of it like building a bridge, right? You've got 2 sides of a river, and you want to get from one to the other. So how do you build a bridge? And I don't know, I always think about it that way. One time I was teaching this course in a room that had like some civil engineering class in there before me, and they were like doing some calculations on bridges or whatever. So there was always these bridges on the blackboard before I got into the room. Okay, so I don't know anything about building bridges, but if I want to build a derivation, I kind of have two ways I can go, right? I can start on one side of the river and start building my bridge and hope that I reach the right place on the other side. Or I can start on the other side. So I can start with X, I can start with the input string, and I can start, I can build a bridge that way, starting with X and going backwards in the derivation, adding derivation steps in reverse, and hope that eventually I hit the start symbol. Okay, so those are 2 classes of parsing algorithms. But by the way, I'm sure if you're actually building a bridge, you probably start on both sides and hope to meet in the middle. I don't know of, actually, I guess there are some parsing algorithms that kind of do that. But anyway, I don't want to get into that. It probably works well for building bridges. Okay, so we start here. Start at the start symbol, build up a derivation, hope it hits, hope it ends up with the input string or the other way around. And you can think of that in terms of the parse trees that we are building, right? And so I like to draw parse trees as triangles because they kind of have a triangular shape. So, the parse tree that I'm going to end up with is going to look something like this. It's going to have the start symbol at the top of the tree, at the root of the tree. And, in computer science, the root of the tree is at the top. I know in biology, it's the other way around, right? The root of the tree is at the bottom. But anyway, if I'm building the tree, I can start at the root and kind of grow the tree towards the leaves. And so, if I'm doing it this way, this is called top-down parsing. Or I can go the other way, right? I can go bottom-up parsing. Right. So I'll draw the same parse tree again, but the question is, how are we building that tree? Do we, start with a node for S and start adding nodes below it? That would be top down. Or do we start with nodes for the input string for X and start kind of putting additional nodes on top of them until we eventually end up with the tree? All right, and we've got a question. So, are there programming languages where instead of writing the source code as a sequence of terminals to build a tree bottom up, you manually build a tree from the top down? So I guess you're asking, are there languages where instead of writing the code, so X is the code, you would actually in your, let's say in your IDE, you would build you would start with S, and your IDE would ask you, okay, how do you want to expand S? So you'd be actually writing the tree in your IDE rather than the string. So I just sort of. I think it probably hasn't caught on very much in terms of forcing people to write the entire tree. I mean, you kind of are indicating the tree by using parentheses and braces and so on. You're telling the parser the structure, but really traditionally it's the parser that discovers the tree. One place where this kind of thing does happen is in languages with very fancy type systems. So I'm thinking of languages like Agda and Idris, where the types of an expression determine a lot about what that expression might be, and so there's some programming environments where you start with the type of an expression, and maybe in many cases there's only a small number of possible trees that you could use to create an expression of that type, and so there's editors that actually say, oh, you're looking for something of this type. Okay, well, here's the three options that it could possibly be. So pick one, and partly, it's kind of like the editor is trying to help you cover all the cases. So and often these are languages that are used for theorem proving. And so in that case, the program is actually not a program, but a proof of some theorem. And so here it's the editor trying to help you write that proof by saying, okay, well, here's the only two things that could possibly work. Which one do you want me to try? So yeah, look up, look for videos, not now, but after the lecture. If you look at Idris or Agda, or if you take CS444, I guess it's kind of going backwards, right? If you're already in 4th year, but maybe you're not already in 4th year, and maybe you haven't taken 245 yet. So yeah, anyway, okay. I think that's a bit of an aside. So, okay, so we want to build the tree. We can build it top down or bottom up, as sort of those are the general techniques. And I'm going to look specifically at LL parsers and LR parsers, and we'll see what that means soon enough. But the nice thing about those parsers is, aside from ensuring that your grammar is unambiguous, they parse in linear time. And so if you're at linear time in the length of x, and so if your program that you're parsing is long, it's nice to have a linear time parser. So we're going to specifically look at linear time parsers. And so our top-down, our example of a top-down parser is going to be the LL parser, and the bottom-up parser is going to be LR. But the thing that okay, so we're going top-down or we're going bottom-up, but in both cases we're going to look at the input, not all at once, but one symbol. So in our case, one token at a time, right? So we're going to look at the input from left to right in both cases, and actually that's what the L in LL and LR stands for, is we're looking at the input from left to right. If you had to look at the input all at once and keep it in some data structure, it would be hard to make the parser linear time in the length of the input, right? If it has to, take the whole input and now start manipulating it, you're going to quickly get into quadratic or more behavior. Yeah, right. Yes. So yes, we are trying to. We're given x and we're trying to build the tree. So all right. So if I'm going top down and I'm looking at the input from left to right, then what I really have to do, and I like to draw this line here. So the line is sort of the division between the part of the parse tree that I have built already and the part that I will eventually build as my parsing algorithm progresses, but I don't, I haven't processed that part of the input yet, so I don't have that part of the parse tree. And so the line kind of goes this way. Over time, it moves along, and basically everything from the start symbol, kind of all the way down to the first token in the input, you have to build right at the very beginning, because you want to process that first token in the input, and then do everything you need for it, and then forget about it and start moving rightwards through the input. Okay, so once again, above the line is the part of the parse tree that we've built already, and below the line is what we haven't built yet. Okay, and so as the line moves, we're just building nodes along this boundary, along this red line. For our bottom-up parser, right, and so if we didn't care about the left to right, the line would be kind of horizontal, and it would start here and it would move downwards. But because we're also reading the input, the line kind of moves this way. For our bottom-up parser, well, again, if we saw the whole input at once, we would have the whole input, and the line would go upwards, and we would build stuff on top of it. But as we are building the tree, we are also seeing more and more of the input. So I draw the line like this, and I put the arrow here. So if we've seen a little bit of the input, we need to build all the piece of tree that goes above that part that we've seen. But then as we see more of the input, we can build more nodes on top of the subtrees that we've already built. Okay, so this is the general, how these algorithms are going to run. All right. Yeah, all right. Okay, and so we are going to look at both LL and LR, but I'm going to focus more on LR. And why, why am I going to focus more on LR? Well, let's look at an example. Okay, so and I'm going to use an example expression: 3 minus 2 minus 1. Okay, so you could take this as an arithmetic problem. What is 3 minus 2 minus 1? It could be one of those viral Twitter things where people argue. So let's see. If I take 3 minus 2, okay, that's 1 minus 1, that's 0. So you want this to equal 0. And someone on Twitter might say, well, 2 minus 1 is 1. And so then 3 minus 1 is 2, so this should equal 2, right? But we're all mathies here, right? So we know that subtraction should be left associative. So you should do the 3 minus 2, and then you should do the minus 1, and not 3 minus brackets 2 minus 1. Okay, so the tree, the parse tree that we want for this expression should have this kind of a shape, right? To force you to do the 3 minus 2 first. That's the tree that we want to get out of this. But now, let's say I'm using an LL parser. Am I going to be able to get this tree? Well, if I draw my little red line here, so the way that the parser works is, at the very beginning, I need to go from my start symbol, and I need to build this whole spine of the tree that is going to take me down to the 3. And so far, I've only seen the 3, so I don't know what else is coming, right? It could be, 3 minus 2 minus 1, or, maybe I've seen the 3 minus, but I haven't seen, the 2 minus 1. And maybe later on it says minus 0, but if it says minus 0 there, then actually my tree would have to look like this, but I have to guess how big this spine of the tree is going to be as soon as I see that 3. Okay, so this is a sense that a top-down parser needs to make a lot of decisions to go from the start symbol, all the way down to the input string right away when it has seen only a little bit of the input string. On the other hand, if I had a bottom-up parser, I can do more. So so this is the tree that I'm building, and so when I see the tree, when I see the 3, I can just build this part of the tree. And when I see the 2, I can add a node on top of what I already have, and I never really have to go to the start symbol until the very end, until I've seen the entire string. So if I then see the minus 1, I can build the rest of it. And if someone goes and adds minus 0 to the end, well, that's fine. I can add that on afterwards. So in a sense, the bottom-up parser has more information, or it can delay the decisions until it has seen more of the input. Okay, so my top-down parser, it cannot parse any grammars that force left associativity like we need for subtraction. So LL A not left associative. And that's kind of annoying because lots of common operators like subtraction are left associative, and so you want to be able to parse them. But if you use this kind of parser, then you could parse it write associatively, you know, get the wrong parse tree and then fix up the tree later. And so that's, you know, you can do that. It's just a tree data structure. You can change the data structure, but it adds an extra step. It adds a bit of complexity in terms of, you know, translating the structure that's specified by the grammar to a different structure that you have in your parse tree. So I'm going to kind of focus instead on LR and bottom-up parsers. And, you know, the question I always get is, okay, so if LL is not left associative, can LR be right associative? And the answer is yes. So an LR parser can parse, you know, both left associative operators and right associative operators. It's just a matter of it has more information about the input before it has to commit to building the top parts of the tree. So I'm gonna, you know, I focus more on LR parsers, but we're gonna look at LL first because one, it's simpler, and two, some of the concepts that we see in LL are going to show up in LR as well, and so it's helpful to learn those concepts in the simpler LL parser first, so that we, you know, understand the concepts before we do the more complicated LR parser. How am I doing for time? Okay, I'm running time. Okay, so all right, I've got I think a good question. So if we're assuming the grammar is unambiguous, then associativity shouldn't be a problem for the parser. Okay, so if the grammar is unambiguous, then every parse tree will, then I mean, for any given expression, there's only going to be one parse tree, which means that, you know, an expression like this with subtraction will either be left associative or right associative, but the grammar has, like the design of the grammar imposes one or the other, and you know, the parser can't accidentally parse it right associatively if the grammar says it should be left associative. Okay, so if you want a unambiguous grammar to specify the associativity, and then if the parser is following the grammar, it's not going to mess up the associativity. The problem with the parser is, you know, I should so I should really rephrase this. So LLK parser cannot parse a left associative grammar. Okay, so if I have an unambiguous grammar, then the grammar either makes subtraction left associative or it makes it right associative, but not both if it's unambiguous. But if it makes it left associative, then an LL parser won't be able to parse that grammar. So, you know, lots of grammars, and in particular, the grammar that you probably want for your Java compiler or your Juice compiler, you probably want it to have rules that are left associative. And so you probably want a grammar that an LL parser won't be able to parse. Okay, so yeah, I mean, it's good to clarify that. Okay, so LL parsing. All right, so how, I mean, I only have a few minutes, but let me, you know, let's at least start looking at, you know, an LL parser. And I'll have to continue this next time, but, you know, let's at least start, right? So, okay, so it's top down. So that means we start with the start symbol S. So I'm going to use a variable alpha, and I'm going to assign it S. So you can think of alpha as this red line here. Okay, it's sort of the edge of the the kind of the boundary of the parse tree that we haven't built yet, or between the built part and the non-built part. If you think of the parser as building a derivation rather than a parse tree, alpha is sort of this intermediate point in the derivation. So we've built sort of this part of the derivation up until alpha, and then we haven't built this part yet. Okay, so we initialize alpha to s, and then we do some wishful thinking. So repeat until alpha equals x, right? We're going to build the derivation until we get to x, until we get to the input. Okay, and so, what do we do inside this loop? Well, let's say we find some production rule A goes to beta. So A goes to beta is in my set of production rules. I guess I'll say find some production rule in there, and then we're going to replace A with beta in alpha, right? So I'm going to take alpha, and if it has an A in it, I'm going to remove the A and put beta in its place, right? So that's how I defined the directly derives relation. It's basically saying if there's a production rule like this, then within your current derivation, one step that you're allowed to take is find an A somewhere inside alpha and replace that A with beta, and then that becomes your new alpha, your next step in the derivation. Okay, so this is a very vague sketch of the algorithm, and of course we have to fill in more details. Let's see. I guess I can do a quick example, and hopefully the example is going to help us see what details we need to add, right? So for example, okay, so here's going to be my grammar, and I have to make sure I have an LL1 grammar. So I'm going to have E goes to AE prime, and then E prime goes to plus A, or E prime goes to nothing, right? I can write that as epsilon, but here the epsilon just means I have an empty right-hand side. It's like the empty string. So here's my grammar. It's an LL1 grammar. It's also a very simple grammar. What language does this grammar specify? Well, from E you have to go to AE prime. So it has to start with A, and then the E prime can either be plus A or epsilon or nothing. So basically the language of the grammar, I can write it here, is A and A plus A. Okay, so this is a language with two words. I've called the non-terminal E because it's kind of like expressions, right? A and A plus A are two expressions in terms of the variable A. But it's a really simple grammar just for the sake of example. And all right, and I've got 1 minute to do a derivation. So let's say my input is A plus A. Then the algorithm is going to set alpha to the start symbol. So I'm going to have E, and then each time through the loop, I'm going to apply one of the production rules. So here, E, I'm only allowed to change it to AE prime. So I'll have AE prime. And then the second time through the loop, I'm going to look in my grammar. And now there's two production rules. So I can either replace E prime with plus A or with epsilon. And since the input is A plus A, I want to take the first option and replace E prime with plus A. And then I will get alpha being A plus A, which was my example input. And so the algorithm will be done. So this is how the algorithm will go through, building the derivation. Now, the part that I, hand waved over was here I had the choice, right? Do I use this production rule or do I use this other production rule? And I kind of said, well, it's obvious the input is A plus A, so it's obvious that I should pick the first one. But this is exactly what we're going to have to add to the algorithm when there are multiple production rules that could work. Which one do you pick? So that we're going to look at on Monday. So we'll how to modify the algorithm to decide which production rule to pick. And I'll just say one more thing. So a grammar is going to be LL1 if I can find an algorithm where the choice of rule is going to be unambiguous. So where at any point in the execution of the algorithm, I'm going to be able to decide, oh yeah, definitely the right rule is this one and not that one, or the other way around. So if I ever have a grammar where the algorithm, wouldn't know which rule to pick or would have to try both, then that wouldn't be LL1, and I wouldn't be able to implement it efficiently, because to implement it, I would have to try both rules, which would mean, possibly backtracking, and it wouldn't be linear time. Okay, so now I'm over time a bit. So we will continue this on Monday. Any more questions here? Okay. So what is the relationship between which kinds of associativity an LL or LR parser supports and which kinds of recursion it supports inside the rules? Yes. So the rules determine the associativity. Or the recursion in the rules determine the associativity. So if I had well, let's see. So if I had a rule like expression goes to expression minus a number, right? Then, what kind of tree is it going to build? Well, it's going to build this left associative one, because on the left side of the minus, you're allowed to have an expression, but on the right side of the minus, you're only allowed to have a number. And on the other hand, if I had a grammar like this, where the recursion is on the right, so the E, the expression, is on the right, then if I if I have the string, well, let me do it here, right? If I have the string 3 minus 2 minus 1, then I kind of have to parse the number minus an expression, and then recursively I can say this expression is a number minus an expression. Oh, and I guess in both cases I want to also say that an expression is a number. Okay, so yeah, so the way that the recursion appears in the grammar determines the associativity of the tree that you get for the expression. If I had a grammar where I said an expression is an expression minus an expression, so if I said E minus E, then I'd have an ambiguous grammar that could be both left associative or right associative, you know, so it could build different trees for the same expression. All right. Does that answer things? Yeah. All right. Any other questions? Okay. Okay. Well, then have a good couple of days. Have a good weekend. And we'll get back to LL parsing on Monday.